So if you're looking at this problem going, I don't remember doing this, like what the hell's going on here? I'll draw you a picture of what we're doing here. What we're doing is this. If you start with the function f, right, it has some graph. If you take the derivative, you get its another graph, which is f prime. And if you take the derivative again, right, you get f double prime, right? That's what the derivative does. What we're doing here is I'm giving you this, right? We're starting here. I give you some information about I give you what the second derivative is, and then we have to go backwards, find the f prime, and go backwards again and find f, right? This is f. That's what we're searching. That's what we're trying to find. But the problem is that every time we go backwards, it's an antiderivative. We have a plus c, and so it gives us a family of functions. And the only way to nail down exactly what function it is if I give you some information about that family. And then you go back again, you get another plus c, and then I have to give you some information so you can nail down exactly which function it is, which is why I give you this. That look familiar? It should, but you know, that's what we're doing. So let me start with the second derivative. Let's go backwards, right? We're going to try and find the first derivative. So we're going backwards. That means I have to take an antiderivative of that, right? So I technically could write this. This would be correct. This would be correct notation for doing this. I'm trying to find the antiderivative of that, right? That's what that notation means. If I want to go from f double prime back to f prime, I have to do the antiderivative of that. Now that antiderivative is going to be clean. This is not U substitution, right? Because you have three terms, right? Separated addition, subtraction. Each one of these is either a constant or some x to a power. So we should be able to go backwards pretty clean. What's the antiderivative of 1? X. Why is it x and not u? Why is it x and not u? What's our variable? See? That's telling you what your variable is, right? If this said du, what would the antiderivative of that be? U, right? Okay, so that keeps track of your variable. So here we've got x, and then minus 6, I'll bring that for the ride. What's the antiderivative of x to the first power? 1/2 x squared. Okay, plus 48 times 48 came for the ride. What's the antiderivative of x squared? 1/3 x cubed. We're done with the antiderivatives, right? Plus c, some number we don't know, right? Now I'm going to clean this up before I do anything else. This is going to be x minus 3x squared plus, let's see, that goes in there 16. 48 divided by 3 is 16. X cubed plus c. So this is what I know about the derivative so far, right? The derivative of this function, right, is this, which is a family of functions because I have plus c, right? So it's all these functions. They all look like this, but then they're just moved up and down. Infinite number of answers. But I'm given some information about that derivative, right? Right? So I say, but f prime of 0 must equal 2. That means when I replace all my x's with zeros there, I should get what? 2. Right? When all the x's in this function get replaced with 0, it should spit out a 2. So I replace all the x's with 0, and it kills this, nothing's there, and we just get c as 2, don't we? Now I know exactly what function we're talking about, right? I know exactly which one it is. So here's what I can say. F prime of x, without a doubt, is the function x minus 3x squared plus 16x cubed plus 2. I'm going to box it. That's not my final answer, right? I'm halfway through the problem because I have what f prime is. I need to do the exact same procedure, go back one more time to get f. Y'all with me? Well, in this problem, it's going to turn out that way. Be careful, all right? Because what students will do is they'll say, hey, I found a shortcut to do this problem. When you get to this point right here and you're trying to figure out what C is always just that number 2, right? That only works if this is a 0. If this is 1, then this would be what? You'd have to plug 1 in here instead, right? So you would get what? 1 minus 3 plus 16 plus C equals 2. And when you solve for C there, it's not going to be 2. All right? So just be careful, because on the final, it's most likely that one of these is not going to have 0 right here. It's going to be some other number. So don't skip this step, right? You're going to have to work it out. Do y'all understand what I'm saying? You know what? In fact, let's change the problem. Let's make that a 1. Let's make it a 1. And you know what? Let's change this to a 4, just for fun, okay? I'm modifying the problem. All right, but we know what f prime is, right? All right, so now, let's find f. F will be the antiderivative of that. Dx. And now I'm going to play the same game that I just played. I'm going to do the antiderivative of each one of those terms one by one, right? One by one. This is going to suck. I can already see this is going to suck, but okay, it is what it is. Let's do it. What is the antiderivative of x? 1 over 2x squared. Okay, what is the antiderivative? Let me see, I'm going to write minus 3. What's the antiderivative of x to the second power? 1 over 3x cubed, right? Plus the 16. What's the antiderivative of x to the third? 1 over 4x to the fourth, right? Are y'all getting that power rule? And then plus, what's the antiderivative of 2? 2x, right? 2x. And then plus what? Some constant, right? And I told you, class, usually we don't use C again because we already solved for C, didn't we? So use some other letter. We usually use capital D, right? And that's what we know about F so far, right? We've got F within a constant. We're almost there. We just need to figure out what D is now, right? If I know what D is, I'm in business. But I have this information right here. Do y'all see how if I had left that as a 0, do you see how easy it would have been to plug 0 in here? And then D would be whatever that number is. But here it's a little different, right? So I know, but f of 1 equals 4. And that means when I plug in 1, 1/2 times 1 squared minus, oh, this right here is a 1, isn't it? 3 times a third. I should have done these first. That's a 4, right? That's 16 divided by 4 is 4. 3 divided by 3 is 1. So I plug in, let's see, 1/2, I plug in 1 here, 1 squared, then minus 1 cubed, and then plus 4 times 1 to the fourth, plus 2 times 1, plus D. That must all equal what? 4. Right? Just plugging 1 into the function. I guess it's not going to suck too bad. It's not going to be great, but this is going to be 1/2, right? That's minus 1. That's plus 4, because 1 to the fourth power is still 1. Plus, this 2 times 1 is 2, plus D must equal 4. 1/2. Let's see. These together, these 3 together, 5. Plus 5 plus D equals 4. D equals 4. Take away the 5, take away the 1/2. So just bringing those to the other side. That means D equals these two together, -1, take away a 1/2. And you can get a common denominator there and put those together. D equals -3 over 2. negative 3 halves. So my final answer is f of x equals, and it was this line right here, right? But I didn't know what d was. So it's this line. It's 1/2 x squared minus x cubed plus 4x to the 4th plus 2x minus 3 halves. Final answer. You could actually check this answer if you wanted to. If I plug 1 into this, what should I get? If I plug in 1, what should I get? 4, right? If I take the derivative of this, right? Take the derivative of this and plug 0 in, what should I get? 2, right? And if I take the second derivative of this, it should be that. All right, good? What else? 13. No, but y'all aren't asking me anything on the other stuff? Okay. All right. 13, limits. Y'all are such a quiet group. Are y'all going to do a study group at all? Are y'all in contact with each other at all through, like, what is that thing, Discord? Or do y'all have anything, group me or anything? Are y'all going to get together and study, anyone? Or y'all are all just going to wing it? Yeah? All right, 13. When I was in college, what we would do is we would, if we ever got a review for anything, we would divide and conquer. So we would have a study group, and it'd be like, maybe it's like 20 problems on the review, and everyone would say, okay, I'm going to go make sure that I know how to do these. And then when we got together in a group, we would just like go through them, and one person would like not teach the others, but like walk through and be like, yes, this is the right answer, you know? But limits. So we did limits in the beginning of class. They were kind of brutal. And then later we got L'Hopital's rule, right? And L'Hopital's now this like great thing we have. We can use it whenever we see 0 over 0 or infinity over infinity, right? So here, when I take this limit, x goes to infinity. On top, x squared, that goes to infinity. And on the bottom, well, you have to know what the natural log function does as x goes to infinity, which means you should probably know what the graph of natural log looks like, which I think I've done enough of it. Hopefully you are comfortable with this. What's the limit as x goes to infinity of this function? Infinity. The function, as you go out to infinity, the function goes up slowly, goes up and up forever, right? That's different than me saying what's the limit as x goes to 0 from the right. If I say what's the limit of, as x goes to 0 from the right, it actually drops down to negative infinity, right? So you have to pay attention to what you're approaching here. We're approaching infinity, going out that way. That means the graph goes up. So the bottom goes to infinity as well. Now, just for the sake of discussion, if it had gone to negative infinity, if it had, could I still use L'Hopital? Yes. L'Hopital just requires infinity over infinity. It does not matter plus or minus. All right, so I'm allowed to use L'Hopital here. And so I'm going to go right to it. I put a little L over that equal sign. And now L'Hopital says I take derivative of the top and the derivative of the bottom separately. See, it's the only time when we take derivatives that we don't do quotient rule, right? L'Hopital's rule is what you wished quotient rule would have been in the beginning, right? Derivative top and bottom separate. But so derivative of x squared is 2x, and derivative of natural log of x is 1 over x. And now don't go do your limit again. Clean this up. Because this is the same, dividing this by a fraction, maybe it's better if I look at it this way. If you look at 2x over, look at the top as 2x over 1, look at the bottom as 1 over x, right? That's kind of what we have here. 2x can be written as this, and then the bottom is 1 over x. Then I can just flip, right? Like that. And if I flip, then I get equals, no L'Hopital, just me flipping. I should just get 2x squared, shouldn't I? And what happens to that as x goes to infinity? Goes to where? Infinity, right? We're done. That's not an indeterminate form. Indeterminate forms are things that we can't tell what's going on, like infinity over infinity, or 0 over 0, or 0 to the 0, or infinity to the 0, or 1 to the infinity, or infinity minus infinity, right? You have that sheet you're allowed to bring that has all your limit forms on it, right? Top left corner are all your indeterminate forms, right? This is not an indeterminate form. If something goes to infinity, it goes to infinity. Done. Questions? Next. 12. On the other one? Yeah? Okay, number 12 over here. Okay, increasing, decreasing, all that. Okay. So notice on this review, the increasing, decreasing, concave up, concave down. Notice that I have, notice the compassion in the function that I'm giving you, right? It's just a nice polynomial, which means that you are going to have no problem differentiating that, right? No problems at all, I hope. So I give you a function f of x equals 5x to the third minus 3x to the fifth. All right, where's the function going up? Where's it going down, right? Increasing, decreasing, that's part A. Find the local max, local min. That's part B. Where's the function concave up, concave down? That's part C, right? Inflection points, and then I say sketch it. We don't have to sketch, right? There's no sketching. We're not doing sketching. So how do we do this? How do we figure out where a graph goes up and down? Tell me in words what we do. This would be good for a reference sheet. How do I determine where a graph goes up and down? Find derivative. Find your critical numbers. Once you get those critical numbers, number line, test points, exactly, perfect. That's what you want to do, right? We're going to do that. And then after we do that, we're going to take the second derivative and do the same thing, and that'll do concavity. That's it. Should be pretty straightforward. I'm going to need the derivative first. Let me get that derivative. The derivative of this is 15x squared plus 15x to the fourth. That's just using our power rule. And so now we find the critical numbers here. So we set this equal to 0, and then we figure out where it doesn't exist. So where is this derivative equal to 0? All right, well, all I have to do is set it equal to 0, and like I said, I made it real nice and pretty for you. You can factor that, right? GCF, greatest common factor. They both have a 15, they both have an x squared. Factor it out. You'll be left with 1 plus x squared equals 0, right? Oh, I'm sorry, that's a minus in there. I apologize. Minus. Given how I feel, the fact that that's only the second thing I've done wrong today makes me feel better. I think it's sleep deprivation. I think that's what's going on with me. I have to take my daughter to school every morning. I have to get up at 5:30. But my wife works these 24-hour shifts. So when she's home, she only works like once a week. So when she's home, she like stays up till 4 o'clock in the morning. So I don't want to go to bed because she's home, right? And it's like it's messing me up. I need to somehow get better at this. Or not teach 9 a.m. classes. There's a solution.
Is she a nurse?
She's a PA.
Oh, yeah.
Yeah, so she works with kids that have open heart surgeries. So when they come out of surgery, she just manages them. Yeah. Okay. She saves lives. I ruin lives. No, I'm kidding. Yeah? What do we do here?
So
Each factor equal to 0, right? Y'all get exhausted at the end of the semester, don't you? Like y'all feel a little worn down at this point? Yes? I do too. I feel this, I get the same way. I'm glad I don't have to take a test next week. I'm just messing with y'all. All right, let's go. So 0 and what? We get some answers here. 0, all right, that's the only solution here. And then here, a couple of ways to solve that. You can move the x squared over and do square root on both sides, right? If you do that, you have to do it plus or minus. Do not forget plus or minus. The other option is difference of squares. Factored is 1 plus x, 1 minus x. So depending on you, you're going to get those two answers, right? Plus or minus 1? Yeah? All right. With those, I draw a number line. I plot these critical numbers. And then pick test points. Yes?
Did we have to find where x?
Oh, yes. Where it doesn't exist. I glossed over that because this is a polynomial function, so it's defined everywhere. But yes, I should have technically said that. This derivative doesn't exist, right? No worries there. I was distracted by myself there, talking about other stuff. Sorry. Test points. Here, 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 here. 4 of them, right? 4 of them. And unfortunately, I'm going to have to pick some fractions. At least in here. Over here, I can pick -2. Here, I'll pick -1/2. Here, +1/2. And here, +2. So I circle my test points. And very important step now, where do I plug those test points in? Into the derivative, because the derivative tells us about up and down, right? The derivative is positive, you're going up, negative down. So now I need to take these answers, plug them into the derivative, -2, -1/2, +1/2, and +2. And all I care about, right, is whether or not this turns out to be positive or negative, right? Is it positive or negative? And there's actually a little shortcut. You could plug these in right here, right? You could plug them into this. If you go down to the factored version right here, forget the equals 0, just the factored version of the derivative, it's much easier to plug into that. Because no matter which of these I plug in, no matter which one I plug in, do you all agree that 15 times that number squared, that's positive? So that's always positive. So all that really matters is what this turns out to be. So let's try the -2. What happens if I do -2 squared? 4, and then I'm doing 1 minus 4 is negative, right? So I get negative there. And then what about -1/2? What happens if I take -1/2 and square it? You get +1/4. What's 1 take away a 4th? 3/4. So positive, right? So you get a positive answer there. Look, if you don't like what I'm doing, then just plug these numbers into this, all right? And just whatever answer you get, all you care about is positive or negative. I'm just doing a shortcut. Let's plug in +1/2 in here. 1/4 again, right? 1 minus a 4th is still positive. See, we don't change here. Do you see that that stayed positive, positive? And then if we plug in 2, we should get a negative. So over here at -2, if my derivative is negative, my function's doing what? Decreasing, going down, right? So here I know that my function, my original function, must be going down here. And then when we get to -1/2, that test point, my derivative is positive, which means my function should be going up here. And then when I get to +1/2, I should still be going up, right? And then when I get to 2, I start going down again. Sorry, I shouldn't have said that. At 2, I'm going down. It actually switches at 1, right? That's where it actually makes the switch. And then at -1 is where it makes a switch. So let's answer part A. Part A says, where is it increasing and decreasing? So f is increasing and decreasing where? Well, it's increasing where? Between -1 and 1, right? Between -1 to 1, my function's going up. So -1 to 1. I told you in class, just use open intervals on these. And then it's going down to the left of -1 and to the right of +1, right? So the way I write that is -infinity to -1 union, then 1 to infinity. How's that? Yeah? Part B, local max, and then local min. All right, do we have any maximums? What are we looking for on that chart that we put up there? For a maximum, what are we looking for? Up then down, right? Up and then down, you have to be at a maximum. So that happens where? At 1, right? At 1. So the way I'm going to figure out what the local max is I'm going to take 1 and plug it into the original function. And that'll give me the y value, which is the maximum, local maximum. And if you plug 1 into the original function, you should get 2, right? The local min, the local minimum is where we go down then up, which happens at -1. So if you plug -1 into the function, that's a little harder to do. Let's see, if I make that -1, this becomes -5, doesn't it? And then if I plug -1 in here, -1 to the 5th power is negative, so then it's a double negative, that becomes +3. So you get -5 plus 3 there, which is -2. How are we doing? Oh, this is it. This is the end. We're going to finish this up. Okay, we got the part A and part B answered. Let's answer part C and part D. So for part C, we need to do the same exact method we just did, but on the second derivative. I'm going to go faster. Ready? Second derivative of this is 30x minus, what's that? 60? X to the 3rd. Okay, where's this second derivative 0? Factor out of GCF. 30x comes out. I'm left with 1 minus 2x squared, right? So I pulled out a 30x from both of those. And then I set each of those equal to 0. This just gives you 0 as an answer. This one's a little bit tricky. I'm going to do it this way. I'm going to move the -2x to the other side as a +2x, and I'm going to divide by 2. And then I'm going to take the square root, which means I have a plus or minus. So plus or minus the square root of 1/2 equals x. Then I also have to check, where does the second derivative not exist? That's not a concern because this is a nice polynomial. And I'm going to do another table, just the way I did this one. Maybe somebody on their calculator can figure out what the square root of 1/2 is for me. This is square root of 1/2. Root 2, so it's like 0.707 divided by 2. What do you get? What is it? 0.7? Approximately 0.7 something, and then this one is approximately -0.7. So you got to pick 4 test points again. Something over here, you could pick -1. I'm going to go -2 here. Over here, I'm going to pick +2. And then in here, I've got it, I don't know, I'm going to be safe. I'm going to go 0.1 and right here, -0.1. And those get plugged into the second derivative. And again, I could plug it in right here, right, second derivative, or I could do into this one. It's a little bit easier for me to do it this way. Let's see, I'm almost out of time. So let's try -2 in here. If I plug in -2 right here, I get a negative number, don't I? Okay, what would -2 here squared be? 4, right? Times 2 is 8. 1 minus 8 is negative. So I have a negative and a negative, which is positive. So if I plug in to the second derivative, if I plug in -2, I wind up getting a positive number. Also, I'll skip ahead. When I plug in +2, what happens is you get a positive here instead of negative, but this stays negative. So you get positive times negative, which is negative. And then in the middle, let's see, at -0.1 and +0.1, let's see what happens. So if I plug in -0.1 right here, I get a negative, right? Okay, so that's negative. -0.1 squared is small, right? Real small. Times 2 is small. If you do that subtraction, I believe it is smaller. This is smaller than 1, so you should get a positive here. So you have negative and positive, that's negative. And then if you do the 0.1 here, you should get a positive this time. And what that tells me, if the second derivative is positive, it means my original function is concave up here, then it's concave down, then it's concave down again, then it's concave up. Wait, sorry, hold on, I messed that up. It switches, sorry. It switches. Concave up, and then concave down. All right, so I'm going to stop here, but I'll just talk through the rest. So it's concave up to the left of negative root 1/2, union with 0 to positive root 1/2. And then it's concave down from here to here, and then from here to infinity. And then how many inflection points do we have? What is an inflection point? Anywhere that you have a change in concavity. Anywhere that you have a change. So does it change concavity here? Yes, so that's an inflection point. Here? Yes, that's an inflection point. Here? That's an inflection point. So you have 3 inflection points. For inflection points, all you have to give me on the exam is these values. You don't have to, like, you know, local max and min, I wanted the actual y value. For the inflection, just give me the x values. Okay, well, it's been fun. I'll see you on Thursday, if not before, during office hours or that study session. You know, we'll see how that all goes. Good luck on your other finals. I imagine that our Thursday final will probably be one of your last finals if you're taking others. So good luck and study and have a good weekend.
What size page in the reference sheet?
Your reference sheet, standard 8.5 by 11 sheet of paper, front and back. If you